For decades, everyone thought Voyager 1 was the spacecraft that had already told us everything about the edge of the solar system. It was the first to reach interstellar space, the first to cross the sun's invisible border, and the first human-made object to travel farther than anything we had ever built. But there was one problem. Voyager 1 crossed that boundary almost blind to one of the most important things scientists needed to measure. Then Voyager 2 arrived years later, slower, quieter, and almost forgotten. And what it detected at the edge of interstellar space changed the story completely. Voyager 2 did not just follow Voyager 1 into deep space, it crossed a boundary Voyager 1 could not fully measure. It passed through the edge of the sun's protective bubble with a working plasma instrument, and for the first time, scientists received direct evidence from a region that had only been partly understood before. The data showed that the edge of our solar system is not an empty line in space. It is not a clean border. It is a strange, active, pressurized, shifting wall between the sun and the galaxy. And the most shocking part is this. Voyager 2 found that the space beyond our solar system was not quiet. It was alive with pressure, particles, radiation, magnetic fields, and movement. For years, scientists had models. Voyager 1 gave clues, but Voyager 2 gave something different. It gave direct measurements from the very place where our sun stops controlling space and the galaxy begins. To understand why this discovery matters so much, we have to go back to the beginning, before Voyager 2 was a legend, before it became an interstellar messenger, and before anyone imagined that a spacecraft launched in 1977 would still be speaking from the darkness almost half a century later. Voyager 2 launched from Earth on August the 20th, 1977. At the time, it was not meant to become the most mysterious machine in deep space. It was built for a rare planetary alignment, a once-in-176 years opportunity that allowed a spacecraft to use the gravity of one planet to reach the next. NASA called it the Grand Tour. Voyager 2 was sent outward toward Jupiter, Saturn, Uranus, and Neptune, carrying cameras, detectors, antennas, and instruments designed for a mission that was expected to last only a few years. But Voyager 2 did something no other spacecraft has ever done. It visited all 4 giant planets. It flew past Jupiter and saw storms larger than Earth. It passed Saturn and revealed new details about its rings. It became the first and only spacecraft to visit Uranus. Then it became the first and only spacecraft to visit Neptune. Every planet it passed gave scientists new images, new mysteries, and new data. But after Neptune, something strange happened. The mission did not end. Instead of dying quietly in the outer darkness, Voyager 2 kept going. Its cameras were eventually shut down to save power. Its planetary mission ended. But the spacecraft still had working instruments, and NASA realized something important. Voyager 2 was now heading toward a place no spacecraft had ever explored directly before, the edge of the heliosphere. The heliosphere is one of the most important invisible structures in our solar system. Most people imagine the solar system as planets orbiting the sun, ending somewhere after Neptune or Pluto. But the real influence of the sun goes much farther. The sun constantly releases a stream of charged particles called the solar wind. This wind flows outward in every direction, carrying magnetic fields with it, forming a giant protective bubble around the planets. That bubble is the heliosphere. Inside the heliosphere, the sun dominates space. Its particles, its magnetic field, and its pressure shape the environment around Earth, Mars, Jupiter, and the outer planets. But far beyond Neptune, the solar wind begins to weaken. It slows down. It collides with material from interstellar space, and eventually it reaches a boundary called the heliopause. The heliopause is not a wall you can see. It is not a glowing edge. There is no sign floating in space saying you are now leaving the solar system. But physically, it is one of the most important borders humanity has ever crossed. On one side is the sun's territory. On the other side is the interstellar medium, the thin material between the stars. For decades, scientists wanted to know what this boundary was really like. Was it smooth? Was it violent? Was it sharp? Was it leaking? Did the solar wind stop suddenly or fade away slowly? Did cosmic rays increase immediately? Did the magnetic field change direction? Did plasma outside the heliosphere behave the way theories predicted? Voyager 1 reached this region first. In 2012, Voyager 1 crossed into interstellar space. It became the first human-made object to pass beyond the heliopause. The world celebrated. Scientists had waited decades for this moment. Voyager 1 was farther from Earth than anything we had ever created. It was sending data from a region untouched by any spacecraft before. But there was a hidden problem. One of the most important instruments for understanding the boundary, the plasma science instrument, was not working on Voyager 1 when it crossed. It had already been shut down years earlier because of degraded performance. That meant Voyager 1 could not directly measure the flow and behavior of the plasma as it crossed the heliopause. It could still detect magnetic fields, cosmic rays, and plasma waves, but it could not give scientists the direct plasma flow measurement they desperately wanted. That is where Voyager 2 became more important than anyone expected. Voyager 2 was slower than Voyager 1. It took a different path. It traveled through a different part of the heliosphere. For years it seemed like the second spacecraft, the quieter twin, the one following behind. But Voyager 2 had one advantage that changed everything. When it reached the heliopause in 2018, its plasma science instrument was still operating. That meant Voyager 2 could do what Voyager 1 could not. It could directly measure the plasma at the boundary. And when it did, scientists finally got a clearer look at the invisible edge of the solar system. The first major clue came as Voyager 2 began approaching the heliopause. The spacecraft detected changes in particles. The solar wind particles coming from the sun began to drop. Cosmic rays from outside the solar system began to increase. The environment around the spacecraft started changing, as if Voyager 2 was moving through a doorway between two different worlds. But the data was not simple. It did not look like a clean, silent crossing. It looked more complicated. It showed that the heliopause was a real boundary, but one filled with pressure, movement, and interaction. The solar wind did not simply disappear into nothing. It was pushing against the interstellar medium, and the interstellar medium was pushing back. Imagine Earth inside an invisible bubble. Outside that bubble is the galaxy, filled with cosmic rays and interstellar particles. The sun is constantly trying to hold that galaxy back with its solar wind. At the heliopause, those two forces meet. Voyager 2 crossed that meeting point, and what it found was not calm. It found that the boundary behaves more like a living membrane than a simple line. It is shaped by pressure from the solar wind, pressure from interstellar plasma, magnetic fields, and energetic particles. It moves, it reacts, it changes with solar activity. It can ripple when storms from the sun move outward and crash into it years later. This is why Voyager 2's discovery changed everything. Before Voyager 2, scientists had one crossing from Voyager 1, but it was incomplete. Voyager 1 had shown that cosmic rays increased and solar particles dropped. It had shown that the spacecraft entered a new environment. But without direct plasma measurements, scientists were missing a critical piece of the puzzle. Voyager 2 provided that piece. It showed what happened to the plasma as the spacecraft moved through the boundary. It helped confirm that the heliopause is a true transition between solar plasma and interstellar plasma. It showed that the sun's influence does not simply fade away smoothly. Instead, it ends at a complex boundary where different kinds of space push against each other. But the discovery raised even more questions. The heliopause was supposed to be the place where the solar wind finally loses its power. Yet Voyager 2's data suggested that even at that distance, the sun's influence was still leaving marks. The boundary was not perfectly closed. Some particles appeared to leak across. The magnetic field did not behave exactly as simple models predicted, and the region outside the heliopause was not empty darkness. It was filled with material that could be measured, studied, and questioned. This is what makes Voyager 2's discovery so powerful. It did not just confirm what scientists already knew. It showed that the edge of the solar system was more complicated than expected. For the average person, interstellar space sounds like total emptiness, a black void, nothing but silence. But Voyager 2 revealed something very different. The space between stars contains plasma. It contains magnetic fields. It contains cosmic rays. It contains pressure. It contains waves. And all of these things interact with the bubble created by our sun. In other words, the solar system is not isolated. It is moving through the galaxy like a ship moving through an ocean. The heliosphere is the ship's protective shield. The interstellar medium is the ocean around it. The heliopause is the surface where the shield meets the sea. And Voyager 2 crossed that surface with instruments still alive, sending back data from a place no human being will ever visit in person. That data came across billions of miles of space as faint radio signals. It did not arrive instantly. Every command NASA sends to Voyager 2 takes hours to reach the spacecraft. Every reply takes hours to return. Engineers cannot control Voyager 2 like a drone or a modern spacecraft near Earth. They have to send commands, wait, and hope the machine responds. And somehow, after nearly 5 decades, it still does. That alone is almost unbelievable. Voyager 2 was built in the 1970s. Its computers are ancient by modern standards. It carries technology weaker than devices people now keep in their pockets. Yet it is operating in a region colder, darker, and more distant than anything humans had ever designed for. It has survived radiation, distance, aging electronics, power loss, and the slow decay of its nuclear power source. Its power is limited. NASA has already had to turn off instruments over the years to keep the spacecraft alive. The mission team has been forced to make painful choices, shutting down parts of the spacecraft one by one, saving every watt of energy possible. The plasma instrument that made Voyager 2's boundary measurement so important was eventually turned off in 2024 to conserve power. But before it went silent, it had already done something historic. It had measured the edge. It had given humanity direct data from the boundary between the solar system and interstellar space. And that is why this story matters now. Voyager 2's discovery is not just old data from 2018. It is a warning about how little we still understand. Even after decades of studying space, even after sending telescopes into orbit and probes across the solar system, the true structure of our solar system's outer edge is still mysterious. The Voyagers are the only spacecraft far enough away to tell us what is really happening there. Everything else is either a telescope looking from far away or a model built on Earth. Voyager 2 was there. It touched the boundary, it measured it directly, and what it found forced scientists to rethink the shape, pressure, and behavior of the heliosphere. One of the biggest surprises was that the heliosphere is not perfectly symmetrical. Voyager 1 and Voyager 2 crossed in different directions, and their experiences were not identical. This matters because it suggests the sun's protective bubble may be stretched, compressed, or distorted by the galaxy around it. The interstellar magnetic field may be shaping the bubble. The flow of interstellar material may be pushing against it. The solar cycle may make it expand and contract over time. That means the solar system is not sitting still inside space. It is moving through an environment that affects it. This raises a deeper question. How much does interstellar space influence life inside the solar system? The heliosphere helps shield planets from some cosmic radiation. It is part of what protects the inner solar system from the harshest conditions of the galaxy. If the sun moved through a denser region of interstellar space, would the heliosphere shrink? Would more cosmic rays reach planets? Could Earth's environment be affected over long timescales? These are not simple questions, but Voyager 2's data helps scientists begin to answer them. The spacecraft's measurements showed that the heliopause is not just a boundary of distance, it is a boundary of protection. Inside it, we live under the sun's shield. Outside it, the galaxy takes over, and Voyager 2 crossed that shield. The phrase Voyager 2 crossed the boundary Voyager 1 couldn't measure is not just dramatic, it points to a real scientific difference. Voyager 1 reached interstellar space first, but Voyager 2 arrived with the instrument needed to directly measure plasma conditions. That made its crossing scientifically unique. It gave scientists a more complete comparison between what models predicted and what space was actually doing. And the more scientists study Voyager 2's data, the clearer one thing becomes. The edge of the solar system is not the end of the story. It is the beginning of a much larger one. Beyond the heliopause lies the interstellar medium. It is incredibly thin compared to the air around us, but in space, even thin material matters. A few particles spread across vast distances can create pressure. Magnetic fields can stretch across enormous regions. Cosmic rays can travel through space at nearly the speed of light. Plasma waves can reveal invisible density changes. Voyager 2 entered that environment. It became a tiny machine inside the material between stars, and from there it kept sending data home. There is something haunting about that image. A spacecraft built by human hands, carrying a golden record of Earth's sounds and images, moving farther away every second. Behind it, the sun becomes just another bright star. Ahead of it, there is no destination, no planet, no planned arrival, no rescue, and no return. Voyager 2 will never come back. It will continue drifting through the Milky Way long after its power is gone. One day, it will stop transmitting. Its instruments will shut down. Its antenna will point at nothing. Earth will call, and there will be no answer. But before that silence comes, Voyager 2 has already given humanity one of its greatest gifts. It showed us that the edge of our solar system is real, strange, active, and deeply connected to the galaxy beyond. When scientists first dreamed of sending spacecraft beyond the planets, they imagined discovering moons, rings, storms, and worlds. They did not know that the same machines would one day become explorers of interstellar space. They did not know that Voyager 2 would become the only spacecraft to visit Uranus and Neptune, and then decades later become one of only 2 human-made objects operating outside the heliosphere. They did not know it would still matter almost 50 years later. But it does, because Voyager 2 is not just a machine from the past. It is a bridge between the solar system and the stars. Every bit of data it sends now is precious. Every measurement is from a place no replacement spacecraft is currently exploring. Every signal takes hours to reach Earth, traveling across billions of miles, fading as it moves through darkness, until giant antennas on Earth catch it like a whisper, and inside that whisper is information from the edge of the sun's kingdom. The reason this discovery feels so powerful is not because Voyager 2 found aliens, or a hidden planet, or a glowing wall that humans can see with their eyes. The real discovery is stranger than that. It found proof that our solar system is surrounded by a complex boundary we are only beginning to understand. It found that the galaxy presses against us. It found that the sun's protection has a limit. It found that beyond that limit, space is not empty. It is active, it is structured, it is moving, and it is far more mysterious than the old models suggested. Voyager 2's crossing also changed the way scientists think about Voyager 1. Instead of treating Voyager 1's data as the full picture, scientists could now compare 2 different crossings in 2 different regions. That comparison is extremely important. If 2 spacecraft cross the same boundary in different places and see different things, then the boundary itself must be complex. That means the heliopause may have waves, folds, leaks, and pressure differences. It may shift as solar activity changes. It may react when powerful solar storms travel outward and crash into it years later. It may not be a perfect shell at all. It may be more like a distorted bubble moving through galactic weather. That idea changes everything. Because if our solar system is moving through galactic weather, then the story of Earth is not only the story of Earth. It is also the story of the sun's journey through the Milky Way. It is the story of how our star protects us, how the galaxy surrounds us, and how invisible forces shape the environment we live inside. Voyager 2 gave scientists a direct measurement of that invisible environment, and that is why its discovery still matters. But there is another layer to this story. Voyager 2 did not cross the heliopause in the same way Voyager 1 did. The 2 spacecraft traveled in different directions. Voyager 1 moved northward relative to the plane of the planets, while Voyager 2 moved southward. That gave scientists something incredibly valuable: 2 separate sampling points of the heliosphere. If Voyager 1 was one finger touching the edge of the bubble, Voyager 2 was another finger touching a different part of the same bubble. Together, they helped reveal the shape of something too large for any telescope to photograph directly from the outside. This is one of the hardest things to explain about the heliosphere. We live inside it. We cannot step outside and look back at it. We cannot take a complete photograph of it from far away. We have to understand it from measurements, models, and the rare spacecraft that reach its boundary. That makes Voyager 2 priceless. It is one of the only witnesses. And soon there may be no more witnesses. The Voyagers are aging. Their power sources are weakening. Their instruments are being turned off one by one. NASA engineers are fighting to keep them alive, but physics is unforgiving. Every year the power drops. Every decision becomes harder. Every watt matters. At some point the final signal will come. Maybe it will fade slowly. Maybe an instrument will shut down. Maybe a command will not return. Maybe the spacecraft will continue moving perfectly but silently, no longer able to speak to Earth. When that happens, humanity will lose its only active messengers from interstellar space. That is why Voyager 2's discovery deserves more attention. It is not just a footnote next to Voyager 1's famous crossing. It is a separate, powerful chapter. Voyager 1 opened the door. Voyager 2 walked through it with the tools scientists needed most. And what it found beyond that door changed the way we understand the solar system. It showed that the sun's bubble has a real edge. It showed that interstellar space has measurable plasma. It showed that the boundary is active, not empty. It showed that the galaxy is pressing against us. And it showed that Voyager 1's story was not complete until Voyager 2 arrived. Think about that for a moment. 2 spacecraft launched in 1977. One became the fastest and farthest. The other became the only visitor to Uranus and Neptune. One crossed interstellar space first. The other measured what the first could not. Together they gave humanity its first direct look at the outer edge of the sun's influence. And they did it with machines older than most people alive today. That is why Voyager 2's discovery feels almost impossible. It was not supposed to last this long. It was not supposed to still be sending data from interstellar space. It was not supposed to become one of the most important scientific witnesses in human history, but it did. And now every new look at its data reminds scientists that the universe is not the simple empty darkness we once imagined. Even at the edge of our solar system, there is structure. There is pressure, there is movement, there is a boundary separating the familiar from the unknown. Voyager 2 crossed that boundary, and what it found changed everything. In the end, this story is not just about a spacecraft. It is about the edge of home. It is about the invisible shield around every planet, every moon, every comet, every asteroid, and every human being who has ever looked up at the sky. It is about the line between the sun's protection and the galaxy beyond. Voyager 2 reached that line with one last powerful advantage. It could measure what Voyager 1 could not. And because of that, we now know the edge of the solar system is not silent. It is speaking, it is changing, it is pushing back. And somewhere in that darkness, Voyager 2 is still moving forward, carrying the proof that our solar system is only a small island inside a much larger, stranger ocean of stars.